So far we were talking about individual groups. Now we'll start talking about interrelationships between different groups via this notion of group homomorphisms. So every subject has its object of study, like cell biologist might study cells of bacteria, whatever. So in group theory, the mathematical objects that we study are called groups. But more important for us than studying individual groups is the interrelationships between different groups. So this is probably important in other subjects too. You want to know how different cells of bacteria interact. But certainly in abstract mathematics, it's absolutely true that rather than studying the individual objects, the real focus is understanding the interrelationships between the different objects. So I can explain why this is so in group theory in some sense. So remember, you can think of groups as sets of symmetries of something. So in group theory, you often find that the same kind of symmetry shows up in different areas of mathematics. And when this happens, this establishes a link between these different areas, and this may help you study one side or the other or both sides, so it sort of enriches both sides. And mathematicians really love to build such bridges, and this is how mathematics develops often. The group homomorphism is going to be a function between two groups that sort of establishes a relationship between these two groups, and you can sort of pass information back and forth. If you know something about one of these groups, then you get something about the other group. And maybe these two groups showed up in two different contexts. I can give you one example here, say. It's a rather famous example. If you look at the set of symmetries of the roots of this equation, this is a fifth degree equation, so it has 5 roots. And it's not quite clear what I mean by this, but it can be made sense of. Then that happens to be close related to a certain subgroup of permutation group of 5 letters called A5, or the alternating group of 5 letters. What it exactly means is written here, but it doesn't matter. And it also happens to be basically the same group as the rotational symmetries of this 20-faced die called icosahedron. So in all these 3 cases, it's sort of the same group theoretic structure. It's a group of 60 elements. These groups are not the same. This one appears in, I don't know, number theory or something maybe. Number theory. Or you may say geometry. Yeah. This one is very combinatorial. It talks about permutations and stuff. Whereas this one is very much in the realm of geometry. Do you see that same symmetry shows up? Now, this group, for example, is rather tricky to study. If you give me 2 of these rotations of this 20-faced die, and you ask me what happens when I do them back to back, it's hard to say. But these permutations are very concrete objects. It's much easier to compute. So once you know this connection, how to go back and forth between these 2 descriptions, then you can do some geometry using this combinatorial computation kind. And this is how often group theory is used. And so, for example, we can know something about the geometry and conclude something about the group theoretic nature of this group in this description, and from that get some number theoretic information. For example, one knows that the solutions of this equation cannot be written in terms of the coefficients by using some formulas in radicals and so on. That was sort of a very, very famous open problem for 2000 years. So you can solve cubic equations using cube roots and stuff. Quadratics you learn to solve in school. For cubics and quartics, like degree 3 and degree 4 equations, there are similar but much more complicated formulas. And then for 5th degree, it's so tempting to try to find a formula too. And this people tried for 2000 years and failed. And in 1800 something, Galois and Abel and these people showed that you cannot do it, that in general there is no formula for expressing the 5 solutions of a degree 5 equation in terms of the coefficients, like you express solutions of a quadratic equation as in terms of the coefficients. There is no such general formula. This is an example of a polynomial for which any formula wouldn't work, so to say. And the way this was proved is by trying to understand the symmetries of the roots of these polynomials. And so that's actually the genesis of group theory. This is essentially how group theory started. Anyway, that's some storytelling. Let's get back to concrete stuff. I want a little bit of set theoretic notation. So this is not even group theory. This is just sets and functions. Let f from a to b be a function you call this the domain of the function. You call this the codomain or codomain. Codomain of the function. Let's take some subset of A and some subset of B. Then we write f of A1 to mean all the things you get by applying f to all elements of A1. So it's like all the things in B that can be written as f of A1 for some A1 in capital A1. And we write f inverse of B1 to be all the things in A for which f of A is in B1. Let me explain in a picture. Or maybe here. A, B, you have the function. If you take some subset here, A1, you take these guys and apply f to them, and you get some subset here. That is called f of A1. On the other hand, A and B again, you take some subset of B, start with some subset here, and look for all the things on the left hand side for which when you apply f to them you land inside the shaded part. And take all those things that land in here. That's called f inverse of B1. Notice that writing this does not mean that f is invertible. F does not have to be an invertible function. I'm simply looking for all the things in A for which f of those guys lie in this B1. Okay. So we'll just use this notation. This is called the pre-image of B1 and this is called the image of A1. This is called the image of A1 under F, and this is called the pre-image of B1. Okay, so here's the definition. Let G, H be groups, a function f from G to H is called a group homomorphism if, very simply, it preserves the group structure. So if you multiply and then apply f, versus if you apply f to two things and then multiply, you get the same thing for all A, B, and G. And a bijective homomorphism is called a isomorphism. If we say that two groups are isomorphic, G and H are isomorphic, in notation would be G isomorphic to H if there is an isomorphism F from G to H. Remember, bijection means one-to-one and onto. If you're not thought of one-to-one, onto functions, bijective functions, please review at this point. This means different things go to different things, and everything on the right-hand side is hit by some element. We'll give examples in a little bit. The obvious examples are identity function. So verify that the identity function of any group, this is the function defined by A goes to A. It's the lazy function, the function that doesn't do anything, just spits out the input for all A, is an isomorphism from G to G. You also verify that the composition of two homomorphism is a homomorphism. If F from G to H and G from H to K are homomorphisms, then first apply F, then apply G, so you go from G to K, is also a homomorphism. And if both of them were isomorphism, then the composition is also isomorphism. We'll give examples in a second, but I want to just maybe quote one lemma that illustrates this fact that when you have a homomorphism, you get a link between these two groups. So let F from G to H be a homomorphism. And by homomorphism here, I mean group homomorphism. If K is a subgroup of G, then its image, F of K, the thing that we defined on the left-hand side, is a subgroup of H. If M is a subgroup of the right-hand side group, then its pre-image is a subgroup of G. So if you have a homomorphism from one group to another, if you take a subgroup here, take its image, you get a subgroup here. If you have a group homomorphism, G to H, if you take a subgroup here, take its pre-image, take all the things in D that went there, that would be a subgroup on the left-hand side. So this is the kind of stuff, simplest kind of stuff. I mean that when you have a homomorphism, you can get information back and forth. We'll already use this pretty soon, actually. We'll give plenty of examples next time.